Hello, my dear students. I am Arithras Chakraborty, lecturer in electrical engineering of Sri Ramakrishna Institute of Science and Technology. Today, I am going to discuss about the part 3 lecture of polyphase circuit or three-phase system. So, the first topic is the phase sequence in a three-phase system. So, what is phase sequence? In a three-phase system, the order in which the voltages attain their maximum positive value is called phase sequence. That means the voltage attain their maximum peak value or the 90-degree value. So these are the peak value or maximum value of a voltage, and sequence means the angular displacement between this maximum peak value of the voltages in a three-phase system. There are three voltages or EMF in a three-phase system with the same magnitude, but the frequency is displaced by an angle of 120 degree electrical. So the difference between three peak voltages of three-phase system is 120 degree electrical. Taking an example, if the phases of any coil are named as R for red, Y for yellow and B for blue, then the positive phase sequence will be R, Y, B, Y, B, R and B, R, Y, also called the clockwise sequence. And similarly, the negative phase sequence are R, B, Y, B, Y, R, Y, R, B respectively, and known as the anti-clockwise sequence. Okay, so the negative sequence is just opposite of the positive sequence. So when at first the R phase, then Y phase and then B phase, or Y, B, R and B, R, Y, three phases are lying at an angle of 120 degree from each other, then it is the positive sequence. And in case of negative sequence, it will be RBY, BYR and YRB. Okay. Now, by an image or by a phasor diagram, we can analyze the phase sequence in a three-phase system. So here you can see these are the phasor diagrams and these are the circuit diagram of a phase sequence. So that is A, B, N and C. This is a star connected system. Okay, so here you can see that A is a phase, B phase and C are the phase, and N is the neutral. Okay, so that is the A. So in sequence, that is V, A, N. Neutral is the common point, so A, N, that means that is V, A, N means the maximum voltage of AN phase. Next, that is B, so that is VBN and that is VCN. And in case of the second image, we can see here that is just opposite of that circuit. So that is CNVA. So VCN, first one is then VVN and VAN. So first one is the ABC phase sequence and the second one is the CBA phase sequence. So that is the phase sequence in a three-phase system. Now the balance load. So there are mainly two types of load in a three-phase system. One is balance load, one is unbalanced load. So what is balance load? In an electrical system, balance load means every three-phase wire have a same current flow and total current is equal to 0. That means according to KCL we know in case of a balanced circuit, three currents meeting at a node equals to 0. That means this current must be the same. Okay. That is IR, that means the red phase current, plus IY, plus that means the Y phase or the yellow phase current, and plus IB, that is the blue phase current, equals to 0. If any fault occurs in any line, then this line current is increased and the system go to in unbalanced condition. So that means in case of balanced condition, the current are same. So if there is a short circuit or overload occurs in any phase or any type of fault occurred in any phase, that may be line to line fault, line to ground fault, double line to ground fault, any type of asymmetrical fault occurs if any one of the line, then this balance condition is changed and it will be then unbalanced. So in case of balance condition, we know the voltages are mainly same. From the previous diagram we can see here the value of each phase voltage are same, only the angular displacement is 120 degree electrical between them. So if the load impedance is also same, then we know that I equals to V by Z, then the phase current is also same. Okay, so if the load impedance is unequal, then the line also converted into an unbalanced line, or loads are act as an unbalanced load. Suppose fault occur in R phase, then R phase current increase and system go to unbalanced condition. Okay, so that is the balance load. Now analysis of a balance load. Now you can see here one star connected network and one delta connected network. In this image, this is the star connected network and this is the delta connected network. So in case of the delta connected network, ZA, ZB and ZC are the load impedance, and we know in case of balanced supply these three load impedance are same. So ZA equals to ZB equals to ZC equals to Z del. That means all the impedance are same. That is IL line current equals to root 3 I phase. That means the phase current. Okay, that is the line voltage. It is no neutral is connected, so line voltage and phase voltage are same. So that is the phase voltage. Both are same. A and B. This terminal also A and B, and these are the phase current I phi. So if the Z is equal, that means load impedance is equal and the line voltage is also equal, then, and if the line voltage and phase voltage is equal, why? Because line voltage means the voltage between two phase, this is the line voltage, and phase voltage means the voltage across one phase. So here A and B, these two terminals are the two phase terminal, and this A and B is same as these two terminals, so VL equal to V phase. So the current or phase current is also same, because we know the voltage per phase and the impedance per phase are same, so I equals to V by Z. So it is a balanced condition of delta. In case of star, same thing happen. This ZA, ZB and ZC, these are the three load impedance which are same. So we can write here that in case of Y connection or star connection, ZA equals to ZB equals to ZC equals to ZY or Z star. So in that case, we know that line current equals to phase current, because this current is flowing through this line and this current is also flowing through the phase. So IL equal to I phase, okay, and VL equal to root 3 V phase. VL means the voltage between two phase and V phase means the voltage between one phase and one neutral. So if the phase voltage is same for each of the phase and the phase current is also same, because the load impedance are same. So that is the balance load of a three-phase star and delta connection. Now the unbalanced load. So unbalanced voltage usually occurred because of variation in load. When the load on one or more of the phases is different than the others, unbalanced voltage will appear. Or if the load impedance is unequal, then also the unbalanced voltage will appear. This can be due to different impedances or type of and value of loading on each phase, and as well as for the fault in any one of the phase. Now the vibration of the motor. So what is the effect of the unbalanced load? So in case of a three-phase motor, if the load is unbalanced, then the negative sequence voltage caused by the voltage imbalance produce opposite torque and tends to motor vibration and noise. Okay, if the direction of the torque is changed, we know that from our previous discussion that the negative sequence or negative phase sequence means when the phase sequence is in anti-clockwise direction. So when a motor is running in positive phase sequence, then the field is rotating in clockwise direction, and if the unbalanced condition is arrived, then there is a negative sequence is occurred. So there is a opposite torque is produced and leads to motor vibration and noise. Severe voltage imbalance may even result in motor collapse due to the uneven torque or due to the opposite and uneven torque, and reduce motor life. Heat generated by the unbalanced voltage may also reduce the motor life. So here you can see that is the positive sequence A plus, B plus and C plus, and you see that there is the direction is same, but the value of the voltages is minus. That means A minus, B minus and C minus. That means the sequence is negative. So if we assume that is A minus is A plus, B minus is B plus and C minus is C plus, we can write that the sequence is rotating on the anti-clockwise or clockwise side. Okay, that means if we consider that the positive phase sequence is rotating in anti-clockwise side, then it is clockwise side, and vice versa. That means the direction of the negative sequence is always opposite of the positive phase sequence. We know the forward direction of a motor is always in anti-clockwise direction, so we can write that the positive sequence is anti-clockwise. But if we consider that the positive sequence is clockwise, then the negative sequence is actually anti-clockwise. And if we consider the positive sequence is anti-clockwise, then the negative sequence is clockwise. In that diagram, we can see here the negative sequence is also anti-clockwise, but the value of the voltages are negative. So if we consider the value of the voltages are positive, then the sequence is clockwise in direction. So the direction of the sequence is changed, and due to that reason the motor vibration occur, because the direction of torque is also changed. So that is the unbalanced load. Now analysis of unbalanced load. So here you can see that at first one is the balanced three-phase load where IN equals to 0. This is star connection. This is a, so when this is balanced means the load impedance or load resistance of each phase are same. These are 40 ohm, you can see here. So load current are also same, because these three coils are identical in nature. So the phase voltages are also same. So this current is also same, the phase current. Okay, or you can say that is load current, because these are the loads impedance. So then the three current meeting at a node, the algebraic summation of the current is 0 according to the Kirchhoff's current law, because this is a balanced circuit. Okay, in the second circuit we can see here the A phase is open, that means it is unbalanced. Why? Because this load impedance is 0 at that time. At that time the value of this resistance or impedance is 0. So IA or the A phase current is also 0. So there is a current will flowing through the neutral path. That is the unbalanced load. And in the third diagram you can see here this path is short circuited. Okay, that means the IA current is infinity or very high. So it is also unbalanced in nature. That means when the phase current of each phase is not equal with each other, then this line will be treated as an unbalanced line, or the loads are the unbalanced load. Thank you. That's all for the day.